Hello, and welcome to Computer Sound, a series of lessons on writing computer programs that make sound. This is lesson 1, an introduction to what we're going to be talking about, how the examples will work, and what an audio program looks like. So, what are we talking about? Well, this is about programming audio stuff from a low-level perspective. It's not about using computer programs like Ableton or Maxim SP or even stuff like Super Collider. It's about using general purpose computer languages to write programs that make sound. It's also not about using synthesis libraries like Juice or the synthesis toolkit or I don't know many other ones. I mean, Juice is the big one. It's more like how to write those kind of libraries, or at least how to get started doing stuff like that. So here's what I think you need to know coming into this. I'm not going to teach you how to program in general, but you don't have to be like a super experienced programmer. In fact, learning to work with these kinds of programs is a great way to get some experience with real-time programming and stuff like that. I'm going to be using JavaScript as the programming language to share examples. It's definitely not the best language to write sound programs in. This isn't an endorsement of JavaScript. I'm not going to defend it as a language in general, but it's got one really big advantage for what I'm trying to do here, which is that everybody who's watching this already has all the tools they need to run and debug JavaScript programs on their computer. They don't need to set up any libraries. They don't need to install any compilers or anything like that. They can just look at the example web pages, right-click, view source. I won't be using any React or fancy JavaScript frameworks or minifiers or anything like that. Just easy, straightforward code. So you don't have to have a lot of JS experience. You just need to be willing to read and write that kind of code. A couple more things. The examples I'm going to have are going to be using the Web Audio API, but only a tiny little corner of it. I won't be teaching you much about that API. It's very big and does a lot of stuff. And I'm mostly going to try and sort of get all that stuff out of the way and, kind of wrap it up so we don't have to use it. Don't have to think about it. I'm also going to have some graphics code using the HTML5 canvas stuff, but you won't really need to understand HTML5 canvases to follow the audio programming. And, the graphics stuff I'm going to do is pretty simple. Nothing fancy graphics-wise that should get in the way. And then I'm not going to be diving directly into a lot of digital signal processing or theory right off the bat. I'm more interested in getting started with the mechanical parts of writing these kinds of programs. And you don't really need to know a lot of theory to get some good sounds. That being said, I will talk about this kind of theory more as we go along and as we, have a chance to apply it. And, maybe I'll also be throwing in, at least one like anti-theory approach as a fun little side lesson. By anti-theory, I mean, approaching this without really knowing or understanding the science. It's a avant-garde art thing. So yeah, let's now start. Well, let's now do this first lesson, and we'll start by going to the clipboard and talking about what an audio program looks like. So, all right, what are we trying to accomplish with making sound on a computer? So I'm going to start with the assumption that that you've seen pictures like this. We draw a little graph, and this is time going that way. And we see some shapes, and we say this is a sound wave. Let's make it go all the way, and it keeps going into the future. The idea of this graph is this up-down part is pressure, and over time, and so air pressure changes over time in our ears, and that causes us to hear things. Now, one thing that at least it wasn't obvious to me, but I later realized, is that if you could take this signal over time and change it into an electrical current and send that to a speaker, that speaker would shake in such a way that it would reproduce that same pressure change in your ear, and you would get the same sound. So you can record and reproduce the sound. And if you can produce a squiggly line like this, you will get a sound out of a speaker. And if you give it a different squiggly line, you'll get a different sound. Great. That's great. So if our computer program can produce a squiggly line like this, we can get a sound. However, this is a problem. This is a continuous line, and computers can't really handle continuous things. They deal in chunks of numbers. But what we could do is we could just look at this line at a bunch of different points, say what value is it at each of these points, and then we could send that list of numbers, and our hardware could connect the dots. And as long as we've got a lot of these dots, we'll get pretty good. Now, it's a little hand wavy, right? When I say connect the dots, what it's doing is actually a bit more complicated, and we can go into it later. But what's really important to understand about our program is that's what we're doing. We're going to create these dots, which will translate into our sound wave. Formally, the dots are called samples. So we create samples. We send lists of samples to our audio hardware. So what that's going to look like in our program is we'll have some fixed size, some fixed number of dots that we need to produce. We'll produce those, send them over to the hardware, and they'll say, okay, cool, I'll start playing these. You give me the next chunk. And periodically, our program will get interrupted saying, yo, I'm gonna need another chunk. These chunks usually are all the same size, and these interrupts come at a pretty regular interval. I'm not sure if it's smart enough to interrupt you while it's like halfway through with one buffer. And each chunk is usually referred to as a buffer, but it's an array or a list. It's just give me these samples, give me the next one, so that I can draw this wave shape. And I don't know if it interrupts you in the middle of them or it interrupts you at the start. I would assume it interrupts you at the start. But this kind of structure of program is pretty universal. You're going to get an interruption that says, give me the next buffer, give me the next buffer. And at all points, you have to be prepared to give it the next buffer. Now, how big are those buffers? It depends. But in general, the smaller they are, the harder your program will have to work, because it has to keep jumping over and recalculating. It has to calculate faster and faster and faster as it has less time to calculate each buffer, because it needs to give them faster. But you'll have less latency. Your program will be more responsive. Latency isn't like strictly determined by buffer size, but it's mostly determined by buffer size. If they're bigger, it'll be easier for your program to do, but your program will be less responsive, because imagine as you're getting this interrupt, let's say you click a button right here. Well, you're gonna have to wait till you finish calculating this buffer, and it won't be till this buffer that you'll be able to respond to that button. This structure, callbacks full of buffers, are pretty universal throughout all kinds of audio programs. There are different ways you can do it. You can do it without the callback, for example, but almost all the time you're going to be doing it with the callback, whether you're writing this in Python or C++ or Rust or something like that. You'll usually generate a thing and say, hey, every time you want a buffer, call this function, give me a place to fill it up. And it's no different with the stuff we'll show in the examples. Now, there's a few technical questions to ask, like what kind of value should each of these samples be? And once again, the answer is it depends. They can really kind of be anything, but most of the time that I've encountered, what people tend to use is a floating point number where the maximum and the minimum of how much your audio signal are just represented by 1 and -1 respectively. This has a lot of advantages. It basically means you can generate your signal in any way that's convenient for your algorithm and then easily just scale it into those bounds of between 1 and -1. But, in some situations, it might not be. But for the purpose of all the examples we'll be coding and, sharing on the website, is going to be 1 and -1. And that's pretty much what our audio programs look like. We need to set up, say, here, whenever you need a new chunk of samples, let me know and call this function to fill out a buffer. And we'll see that in the examples. Cool. Okay, thanks for watching part 1. I know there wasn't a lot of material in it, but there was a lot of setup and a lot of explanation about how we're going to go over things. So stay tuned for part 2, where we're going to make oscillators, things which do actual musical sounds at musical pitches, and that should be fun. We'll get some real bleeps and bloops.